Simple steer solver, and let us start with the first behavior implementation, the arrive behavior. Let's start with the arrive behavior because this is a very simple and easy to understand behavior. The goal of the arrive behavior is to steer, let the agent steer against this target point and slow down the agent and stop at this position. This circle here indicates the maximum distance the agent may slow down its speed. It's really simple, the calculation, because we just have to calculate the steering force to get an desired velocity. This is our current velocity, and our desired velocity looks in the direction to the target point, and our steering vector is modifying this velocity in this time step. Let's take a look to the vector math again. We have this equation here, point plus a vector is a point. In our case we have the point position of our agent and our goal position, and what we have to do is just subtract the agent position from the target position to get the vector pointing to the target point. And this is what we have to do for calculation of the desired velocity. We have the target point and we are subtracting the point position of the agent, and this is the desired velocity. Next step we have to do is calculating the difference between the velocity and the desired velocity, and this can be done by just subtracting desired velocity minus velocity. Let's do this in Houdini. First, this is our basic setup, and we have this sub-simulation, and let's enable the initial velocity. This is our basic simulation setup, and create a null in space here. This will be our indicator where is our target position. Call this arrive location, and now let's go into our simulation, sub-simulation, remove the temporary test force, and here we will add our arrive behavior force. Create a new operator type, call it steer arrive, save it into our steering library. Now, so we have our steer arrive type properties here, and first we have to do is defining the parameters our node should have. This is here between this brackets we can define our parameters. This is the up path to our arrival point. This will be the null, for example, and we can also define an initial value, in our case an empty string. Then we need a float variable called break radius, or let's call it max radius, and also add a force scale, as we are able to scale our forces if it is too big, for example. As max radius, let's define initial values, max radius 1.0, and as force scale we use 1.0. Okay, the first thing is We define a variable called arrive. This variable should contain our arrive position. First initialize this position with the origin point. Now we want to translate this arrive point to the null position, and the null position is, in our case, is defined by the op path here. Vex provides us with a function called op transform with an op path. This function returns a matrix and the transformation matrix, and this transformation matrix can be used for translating this arrive position. Transforming a point or a vector by a transformation matrix is really simple. We just have to multiply the point or the vector with the transformation matrix. Let's do arrive is the current arrive multiplied with the op transform of the op path. Let's take a look to our slide. The first thing is, let us calculate the desired velocity. This is the best velocity which points from the agent in the target direction. Create a vector, desired velocity, and remember our vector math. This is just subtracting the point position from the target position. Now we have the desired velocity. But remember, what the arrive behavior have to do is the agent should stop on this target point, and that's why we have to slow down the desired velocity if our agent is within this maximum radius. This means we have to fit our desired velocity within this area, starting from this point to this point, to the target point. On this point we have the full desired velocity, and on the target point we fit it down to 0 velocity. Okay, our desired velocity is first we have to normalize the desired velocity. Now our desired velocity is 0, is 1, length 1, and now we can scale our vector to the desired length. This is a good practice for changing the length of a vector. First normalizing the vector and multiply with the desired length. Okay, we fit now the distance between our agent to the arrival point is length arrive minus p. We could also use the desired velocity because initially this is the same value, desired velocity between 0 and our max radius. If we are 0 means we are already on location. We already arrived the point. It means our desired velocity should be 0, and if we are outside of the max radius, our desired velocity should be our desired velocity length. Now the only thing what we have to do now is accelerate our agent. Let's do this by desired velocity minus the current velocity. This is just the difference between the desired velocity and the velocity. This will be our steering vector. Because our desired velocity could be the opposite direction to the current velocity, and this could result to very big acceleration forces, and we have to clamp our acceleration force to maximum value. Let's do this in the next line of code. Let's limit our acceleration force to 1. Acceleration force is normalizing. Let's do it the same way we did for the desired velocity. Normalizing the acceleration attribute to make it length 1 and multiply it with the clamped length of the acceleration and clamp it between minimum 0 and maximum 1. Test compile was successful. Accept. And now let's add our steer arrive connected and max radius. Let's use 2. Our up path, let's just modify the name of our null to arrive location and change the up path to obj arrive location. Now start and see what happens. You see that all the agents are moving to this target point and stopping at this point. Let's leave this implementation for now and start with a new behavior to demonstrate how we can combine them. Now let's start with another behavior, the separation behavior. The separation behavior is necessary to avoid other agents and not to collide with each other. If you press play and take a look at our arrive behavior again, you see that they are clumping together to one point, and we want to prevent this by implementing the separation behavior. Take a look how the separation behavior works. Here we have an agent and we have nearby agents, and the separation behavior calculates a force away from each of the agents around us and calculates the average force of them. Here the specific forces to the other agents are in gray and the average force is in red. Create a new operator type, call it steer separation, accept, and here we have our initial code. And now what input parameters do we need for separation? Since we have to look up our neighbor points, we need the point cloud lookup mechanism, and so we need a path, a subpath to the points. This is usually the op input path of the current node, but we can add this later into the parameters. Let's just define the parameter PC cloud path and initialize it to an empty string, and the next thing is we need an force scale, and as well as we need a radius for the neighborhood lookup. let's initialize this to 1.0 and the force scale to 1.02. Remember, we have to use our PC open vex function to open a point cloud. The PC open queues the points centered around a certain location and returns a handle. And first create our handle. This is an integer, and our PC open function, our point cloud path, and it queues up the points around a certain location P. This is our location, and based on positions found in a specified channel, and we need the P channel of the other points too. And our lookup should be done within the specified radius, and as we need a maximum number of points, and this is why we want to use all, and we can use a big number for this to cover all points. Now we have to iterate over all points found by the PC open query. This can be done via the PC iterate function. The PC iterate needs the query, the PC open handle. This is our handle, and this function returns 1 while there are points left in the iteration loop, and 0 when there are no further points. So that's why we can this within a while loop, and with this statement we can iterate over all points found by this PC open query. And within this PC iterate loop we can use the PC import function to import the attributes of our neighbor points. What attributes do we need? To keep it simple, let's start with just the point position of our nearby points. Let's create an vector, call it other p. This will be this variable will store the point position of the found point, and PC import, we have to specify our point cloud handle, and our attribute to import, this will be the point position, and store it into the other p variable. Outside of this loop, let's create a vector which will store our final separation force and initialize it to 0. And now we have the other point. We easily can calculate the opposite direction to this point. This is, remember our arrive behavior. This is the same mechanism, just the new separation is the old separation, because we are in a loop and we have to sum up all our forces plus our point position minus the other point, the point position. This will calculate our point, the other point position, our point position minus the other point position calculates this steering vector away from this agent. But let us normalize this value, because this could be too big force too, and what is an important thing too is that the force should be bigger if the point is very close. And this can be simply achieved by dividing the force by the agent's distance. This means if they are far away, the force becomes lesser, and if they are closer, the force becomes bigger. Okay, let us divide by the length of our force. Finally, we have the sum of all separations, but we have to divide it by the number of found points because because we have to calculate the average. So let us create an integer calling neighbors, and each time if you found a neighbor plus plus, this is neighbors plus plus is the same as neighbor equals neighbor plus 1. Just it increments this variable with 1. And after the loop separation, this is the same notation. If I use slash equal, means I use separation is separation divided by this value, and I divide this separation by the number of neighbors. Finally, set axial attribute to our separation, calculated separation force. What we are doing here is not really correct, but I will show you later how we combine multiple forces together, because keep in mind that we have to use different mind algorithms. So, but this I will explain this later in this training. Let's do a test compile. Compile was successful. Accept. And now add our new steer separation. Remove our arrive and add our separation node. In this point cloud path we need to specify the path to the subpath to our point cloud, and this is the node connected with our separation node. This means we can use the op input path expression. First we have to use the op syntax because the point cloud path, the PC open, uses a file name, and if we want to specify a subpath we can use the op syntax, and we can use the op input path from the current node, the first one, to specify. Here we can see if the expression is resolved, it uses the last time step sub, or if I connect the steer arrive, for example, it uses the steer arrive. This is exactly what we need. And now let us start and take a look what's happening. You see that all the points are moving away from the other points. One thing I forgot to edit the separation. I forgot to calculate the force scale. Let us multiply our separation with the force scale, so we can use this force scale too, and here we see separation works basically. But what we are doing next is we want to combine the separation behavior with this arrive behavior. This means we want all the agents moving to this point, but trying to separate from the other points and not clumping on this point. This is what we will do in the next chapter, and the next chapter is covering our first version of a mind algorithm. Now we have two behaviors. We have the steer arrive behavior and we have the steer separation behavior. The next